Hello, welcome to this review video of Elec Eng2CI5. I will go in this video over three examples of first order circuits. I will try to explain I will remind you of a number of concepts that you should keep in mind when you try to solve such circuits. Two of these examples I should mention the handle capacitors and one handle inductors. Okay, let's see how these examples will go. Okay, we have this circuit here. We have a capacitor, and this capacitor has a value of 100 microfarad, 10 to the minus 4 farad. And we have this switch. Before time equal to 0, this switch was opened. So there is no current flowing here before time t equal to 0. But after time t equal to 0, this switch gets closed and this becomes short circuit. Okay, so in analyzing these circuits using the step-by-step method, we will need the initial voltage of the capacitor, we will need the steady state voltage of the capacitor, and we need to determine the time constant tau. So the model we're going to be using is that Vc of t is equal to k1 plus k2 e to the minus t over tau. So now we have to see first the initial conditions before time t equal to 0. At t minus, this is what we call time equal to 0 minus. At time equal to 0 minus, what was the voltage across this capacitor? What is Vc of 0 minus? What was the voltage across this capacitor just before this switch was closed? Okay, so before this, so let's now consider the case where t less than 0, this switch is open circuit and the circuit was at steady state, so the capacitor is open circuit. And we agreed a capacitor, when it reaches steady state, means it's not charging any further, there is no current going through it, and then it effectively represents open circuit. So let's see how the circuit will look like after we keep the switch open circuit and we keep the capacitor as well open circuit. Now we are now trying to calculate the initial condition Vc of 0 minus, the capacitor voltage just before the switch was closed. Okay, so I redrew the circuit again. You can see the switch is opened. Okay, so we are still at the time before t less than 0, so t is equal to 0 minus, and the capacitor is fully charged, so it represents open circuit. There is no further current going through it, but there is a voltage across it. Okay, this voltage is a voltage difference here, VAB, which I have to calculate. So now I have a circuit. This is like any of the circuits we dealt with in this course. We have, let's see how many loops. One loop, we have a second loop here. This is actually one loop, this is open circuit, one loop, a second loop. I have one node, a second node, a third node. I prefer to use nodal analysis here. I found it to work easier. I have to write in the nodal equations at this node and this node and this node. Okay, so the sum of the currents flowing from each one of these nodes is equal to 0. As we agreed before in nodal analysis, you can't write KCL here. Why you can't write KCL here? Because you have a voltage source connecting this point to ground. Excuse me. So what's gonna happen is that you have to write an alternative equation. The alternative equation here is obvious. I can't write the sum of the currents flowing out from here equal to 0, but I can say that V1 is equal to 12 volts because I took this point here as ground. So the voltage here V1 is equal to 12 volts. So this is the first equation I can get. V1 is equal to 12 volts. Now let's talk about V2. In V2 there is no problem in writing KCL. So the current, the sum of all currents flowing out will be equal to 0. Remember that this is one node. Okay, you can see it's shorted. This is one node. So there is one current flowing out. There is a second current flowing out. There is a third current flowing out. So we get three currents flowing out here. So the first one is V2 minus V1 over 3K. The second one is V2 minus V1 over 6K. The third one is V2 minus 6 minus V3 divided by 1K. So these are the three currents I mentioned to you here. What you have to do, you have to multiply both sides here by 6K. So this will be 2V2 minus 2V1. This will be V2 minus V1. This one will be 6V2 minus 6V3 minus 36. Okay, you collect all the corresponding coefficients and replace V1 by 12. If you do this organization, and I recommend that you pause the video for a second and do this simplification, you get this equation here which is 9v2 minus 6v3 is equal to 72. Notice that I got rid of v1 because I know what's v1. v1 is equal to 12 volts. I got rid of it, and it's a constant coefficient. I moved it to the other side, and I added to the 36 I got from here. Okay, so we got the first equation. Now I'm gonna write KCL here. So again, we see how many currents flowing out. One current, a second current. Only two currents flowing out from here. This is open circuit, okay? So this one is V3 over 4K. The current flowing here is V3 plus 6 volts minus V2 over 1K is equal to 0. Okay? So we write this one, and then we write the second equation relating V2 and V3. Remember, we have three nodal voltages we are looking for, V1, V2, and V3. We already know what is V1. Then we need to get two equations between V2 and V3. We already have one equation from node 2. Then the writing KCL at node 3 will supply us with the third equation. So you write KCL as we agreed on the third node, V3 over 4K, this is the current flowing out here, plus V3 plus 6 minus V2 over 1K, this will be equal to 0. If you multiply both sides by 4K and you collect the similar coefficient, this is what you end up having. Minus 4V2 plus 5V3 is equal to minus 24. So if you solve the last two equations using your calculator or substitution or Gauss elimination, any other technique you're familiar with, or using your calculator, you'll obtain these answers, which is V2 is equal to 10.2857 volts and V3 is equal to 3.4286 volts. Notice why am I doing this analysis from the beginning? I would like to calculate the voltage across the capacitor just before the switch was closed. Okay, this voltage here is VAB, is V2 minus V3. I already know what is V2, it's 10.2857. I already know what is V3. If you subtract these two, you obtain that VC of 0 minus is equal to 6.857 volts. So the capacitor is here. You shouldn't forget about this. The capacitor is still there, but we are not showing it. It's still here, okay? But there is no current flowing through it. So we now know just before the switch was closed, the capacitor voltage, which is here equal to V2 minus V3, is equal to 6.8571 volts. Now we move to the second stage. The switch is closed, okay? And then the capacitor voltage will start to change until it reaches steady state. Once it reaches steady state, again, it's going to represent the open circuit as I show it here, okay? So what I'm trying to find in order to be able to use the step-by-step method, I need VC at infinity, the steady state voltage of the capacitor, and this is why I replace the capacitor here by open circuit again. But this is a new circuit because the switch is shorted, okay? So again, I'm going to be using a nodal analysis. From this circuit actually similar than the previous one, and I will show you why. Still, I have V1 is equal to 12 volts. V2 here has been shorted to ground, so V2 here is equal to 0 volts. So I have already two of the unknowns, three unknowns. The third unknown is V3, so I'm going to write KCL here. So the sum of all currents flowing out from this node equal to 0. This one here is V3 over 4K. The current flowing here, remember this is V2, then this is V2 as well. The current flowing out here is V3 plus 6 minus V2 over 1K. This is all is equal to 0. Remember, V2 is 0, I don't have to worry about it. Then you have only one equation in V3. You solve it, you get V3 equal to minus 4.8 volts. Okay, so my target is to get VAB, which is VC at infinity, okay? And in that case, it is 0, it is V2 minus V3, which is 0 minus V3. So it is 0 minus 4.8, so you get that VC at infinity is equal to 4.8 volts. So after you close the switch and you leave the circuit until it reaches steady state, you will see that at steady state, the capacitor is open circuit and the open circuit voltage across it is 4.8 volts. So we have two pieces of information we can use now to get K1 and K2 because we know what is VC at 0 and we know what is VC at infinity. What is missing for us is the parameter tau. Tau is the time constant that the capacitor is going to be using to charge in the new setting that we have right now. to charge or discharge. We don't know really whether charging or discharging. We have to write the equation. Okay, so the capacitor is here. Okay, and now we have to find the Thevenin equivalent or the Thevenin resistance seen between these two terminals. How do we find the Thevenin resistance? As we agreed before in earlier lectures, you have to remove all the independent sources. So this one will be shorted out, this one will be shorted out. You try to find the input resistance between terminals A and B, and this would be your Thevenin resistance. And the Thevenin resistance will determine with using the value of the capacitance. We get what we call the time constant tau, which is R Thevenin multiplying C. Okay, so the last step in my calculation, I removed this independent source here. So this voltage source is shorted, this voltage source is shorted. This is now how my circuit look like. Notice that this short circuit here will get rid of 3K. And if you have short circuit here as well, so if you have a short circuit here, this became short circuit, you will see that also this 4K and 2K has been shorted as well. Because you can see this is all one point now. So what you really have is only point A connected to 1K and another 4K on the other side. This is how really the circuit looks like. Then the input resistance or the Thevenin resistance seen by the capacitor into the circuit in stage 2 is equal to 1K in parallel with 4K. I don't want anyone to tell me that they are in series. This is a very common mistake. Remember, if you bought a source here, if I come and bought a source here at this position, okay, positive, negative, you see that the current that will flow here will split. One will go this way, one will go that way. So they are connected in parallel. So 1K and 4K are in parallel. So if you take this into account, you get R Thevenin's 4K in parallel with 1K. It's equal to 800 ohm or 0.8K. So the tau we're looking for is R Thevenin multiplying C. It's 0.1, this 0.8K, so 0.8 multiplying 10 to the power 3. The capacitor value is 100 microfarads, so it's 10 to the minus 4. If you multiply these two together, you get 0.08 seconds. Okay, so this is now the expression for the capacitor voltage. It's K1 plus K2 e to the minus T over tau. We can get K1 and K2 because we know that at steady state what will be the initial the final condition. VC of infinity is 4.8. So if you put here infinity, T is equal to infinity, you get K1 is equal to VC of infinity, which is 4.8. If you put the value at 0, the value that we got at 0 was 6.85. So this will be K1 plus K2, and you obtain K2 is equal to 2.057. Okay, so we got K1, K2, and we got tau. Then we know what is VC of T. As I explained in class, if you have VC of T, you can get an expression for the current or the voltage anywhere in the circuit. What they are asking really for it in this question, they are asking for V naught of T. So V naught of T, but in the new setting, after we close the switch, what you can see if you take a look around this loop, you will see that VC of T is the voltage between this point and this point, while V naught of T is the voltage between this point and this point. Okay, this is a joint point, but obviously this one and this one are shorted. So this is telling us that VC of T and V naught of T have opposite polarity. So the last step in my solution is that say that V naught of T is equal to minus VC of T, and then I multiply the VC of T I got with a negative sign. So this will be the output voltage V naught of T. It is equal to the negative of the capacitor voltage at any time step. So you can see the capacitor voltage started with 6.857 volts, and then this charged to 4.8 volts, and it will remain at 4.8 volts until infinity. This is the steady state voltage. Okay, let's take a look at another example. We have here a circuit. It has one inductor. The value of this inductor is 1 Henry. And we have a switch. Before time t equal to 0, this switch is opened, so there is no current flowing here. And at time t equal to 0, this switch got closed. Okay, so our target is to find not IL of t. I want to get this current I naught of t. And as I explained in class, if I have the current through the inductor, the single inductor I have in my circuit, I know really the voltage and current everywhere else. Using KCL and KVL, I can get the currents and voltages everywhere. So unlike the approach used by the book, I focus on IL of t, and after I get IL of t, I'm gonna be using it to get the voltage and current anywhere else. Okay, so let's see how it's gonna proceed. First, before the switch was closed, so at time t equal to 0 minus, just before the switch was closed, the circuit was at steady state. Then the inductor represents short circuit. So I'm gonna draw that circuit because we need to calculate IL at 0. We need to calculate the inductor current exactly at time 0. We get it from IL at 0 minus I, the inductor current just before the switch was closed. Okay, so I'm gonna redraw the circuit again. This is open circuit, and this one here is short circuit. The inductor is short circuit. Okay, so this is how the circuit looks like. The inductor short circuit, the switch is gone. This is now how the circuit looks like. This is 4 ohm, this is 4 ampere, this is 2 ohm, this is 3 ohm, this is 6 ohm, this is 12 volts. Our target is find this current, because this current is what we call IL of 0 minus. This is the steady state inductor current just before the switch was closed. Okay, so it's a circuit like any circuit we have solved before. I have here 1, 2, 3 loops. I have only 2 nodes. I prefer to use root analysis. I found it easier. Remember that even though you have a voltage source here, but because it's connected to a resistor in series, I can apply KCL here. There shouldn't be any problem. So applying KCL here, we have how many currents flowing out? One current flowing out, a second current flowing out, the third current flowing out. The sum of all these flowing out currents is equal to 0. This one is V1 minus 12 over 3. This one is V1 over 6 ohm. This one is V1 minus V2 over 2 ohm. Okay, so this is the equation here. You multiply both sides by 6, and you collected similar coefficients, and I advise you to stop the video and do this calculation yourself if you are not sure how I got it. I'm not showing the simplification steps here. You get this answer. I collect all the coefficients of V1 and V2. You get 2V1 minus V2 is equal to 8. Notice that I have to put them in order. In all the equations have to be V1, V2, because if you want to solve them using a matrix method or a matrix calculator, you will have to put the matrix in the proper order. Now let's go at this node here, node number 2. We're going to apply KCL as well. We have 1, 2, 3 currents flowing out. The current flowing out here is V2 minus V1 over 2 ohm. The current flowing out here is minus 4 ampere. The current flowing out here is V2 over 4 ohm. Okay, so these are the three flowing out currents. I multiply both sides by 4, and I collected similar coefficients. 4 by 4 will give me minus 16. Move it to the other side, becomes plus 16. It's collected the similar coefficients, you obtain this one here. So you have one equation in V1 and V2. You have one equation V1 and V2, and notice I put the way I put them. V1 is the first column, V2 is the second column. Okay, so now if you sum these two together, you get 2V1 is equal to 24, or V1 is equal to 12 volts. V1 is 12 volts. You go back, substitute here, you get V1 is equal to 10 volts. Okay, why am I doing this calculation? Because I need to calculate this current. This is the IL at time 0 minus, the inductor current just before I close the switch. So it's equal to V1 minus V2 over 2 ohm. So it's V1 minus V2 over 2 ohm. So it's 10 minus 12 over 2. So it's going to give us minus 1 ampere. So this minus sign is simply saying that the inductor current is actually flowing from here to here. It's flowing from right to left. Okay? But again, as we agreed in class, I already took its reference direction to be this way, so I'm going to keep this reference direction, and I will say the value is simply minus 1 ampere. The next step in the solution is that I have to get IL of infinity. What will happen after I close the switch? So I'm going to create a short circuit here, okay? And then I will try to find what to be steady state of the inductor current in this new situation. So I redrew the circuit after the switch has been closed. Okay, this is how the circuit looks like. And the inductor here, if you reach steady state, which I'm looking for, this represents short circuit. So I can come here and simply replace this inductor by a short circuit here. So this one is shorted, okay? So this one here is short circuit. Okay, and my target is to find the current flowing in this short circuit part here. Okay, so again, this we have this situation here. Notice that because you have this short circuit which is coming from the switch, this left hand part of the circuit and this right hand part became now really completely disconnected. So I redrew the circuit without this part at all. This is how it looks like, and in my calculation I have effectively a short circuit here in this position. So this is really short circuit. So if you have a situation like this one, there is a current 4 ampere, it's flowing this way. I'm just have to clarify the direction. It's flowing this way, and it has short circuit across it. So we can immediately tell that this 4 ampere will flow in the short circuit and it will ignore this resistance. So the current flowing here is actually 4 ampere with this direction. So it is flowing in this direction here, okay? But this direction is opposite to the direction of IL. This means that IL of infinity is equal to minus 4 ampere. Okay, so this is the conclusion of what of this. IL is equal to minus 4 ampere. So now I know what's IL at time 0. I got it from the previous analysis. I got from this analysis IL of infinity, it is minus 4. I need now to calculate tau. Tau is the time constant through which charging or discharging are done. So I have to find the Thevenin equivalent after I replace this inductor by an open circuit. Okay, so I can do that. I can replace the inductor by an open circuit. So if you open circuit this part here, let me see here if I can do that. If I come here and create an open circuit, okay, so I'm gonna erase all this here, and I'm gonna create an open circuit. So I have here this terminal and this terminal, okay, and I will have to get rid of all the independent sources as well in the way we did before. So this current source here becomes open circuit, okay. The current source is gone. So looking between these two terminals, you see only the 4 ohm, and this is really the Norton, because looks like a Norton equivalent, correct? A current source embedded with a resistor. It's really, after you open this one, you see the 4 ohm. So R Thevenin is equal to R Norton is equal to 4 ohm. And we know that the time constant for an inductor, the inductor is 1 Henry, and the resistance it sees into the circuit is 4 ohm. Then tau is 1 over 4. So it's 1 over 4 seconds. So now we have everything to write the complete expression for the inductor current. It's K1 plus K2 e to the minus t over tau. Remember, tau is 1 over 4, so 1 over 1 over 4 will give you 4. So this e to the minus 4t. Remember that K1 is the current at infinity, because if you put t here equal to infinity, this term goes to 0. We agreed that K1 is the time at the current at infinity is equal to minus 4. Then K1 is equal to minus 4 ampere. And from the initial condition that IL of 0 is minus 1, you get K1 plus K2 is equal to minus 1, but K1 is minus 4, then K2 is equal to 3. So this is the expression for the inductor current. It is minus 4 plus 3 e to the minus 4t. Okay, but remember this, in this question they were not asking for the inductor current. They were asking for another current called the I naught of t. So after you get IL of t, we take a look at the circuit and then try to find I naught of t. So here, this is I naught of t I'm looking for. This is IL of t. I already have the expression for IL of t, but you can see if I apply KCL, you can see that I naught of t is equal to IL of t plus 4 ampere. Okay, this is simply 2 currents flowing in are equal to 1 current flowing out. So I simply have to add to the IL of t, which I already got. It is minus 4 plus 3 to minus 4t. I will add 4. 4 will cancel minus 4. I'll end up with 3 e to the minus 4t. So this is the expression for this current flowing here. It starts with 3 at time 0, and then it goes down to 0 at infinity. Okay, and this is expected. Why it's expected? Because as the inductor becomes short circuit, all the current from this source will flow through the inductor. Okay, so and this one here will have nothing going through it, and this is why at the end it at infinity it reaches 0. Okay, let's take a look at one last example. We have another circuit. This circuit have here three capacitors, 600 microfarad, 300 microfarad, 200 microfarad. They are connected with this configuration. Before time t equal to 0, this switch was opened. At time t equal to 0, we close that switch. And our target is to find the I naught of t. And as we agreed, any current or voltage in the circuit can be derived from the state variable that you have. The state variable is the voltage across the capacitor or the current through the inductor. Okay. Now, when you see something like this, you have three capacitors. We agreed before in a previous lecture that a parallel combination or series combination of capacitors can be replaced by a single equivalent capacitor. So these two are in series. So the total capacitance of these two is 600 multiplying 300 over 600 plus 300. Remember that for capacitors, we treat the series connection in the same way we treat the parallel connection of resistors. So these two will give me 600 by 300 of 600 by 300 will give me 200 microfarad. Okay, so now we have 200 microfarad in parallel with another 200 microfarad. Parallel connections of capacitances are treated in the same way we treat series resistances. So the total equivalent capacitance here is 200 microfarad plus 200 microfarad is equal to 400 microfarad. So from now on, for the rest of this example, I'm gonna replace all these capacitances by a single capacitor of value 400 microfarad. Okay, I'm not gonna worry about this again, and I will treat it as just one capacitor, and I will try to do all the other calculations. So first, let's focus on the first stage when the switch was opened. This is open circuit. The circuit's at steady state. So this equivalent capacitor is open circuit. So I'm not gonna, I'll keep this one as open circuit. And my target is to find the voltage across it. Why? Because I need to determine VC at 0 minus. What is the capacitor voltage just before the switch was closed? This will give me the initial condition I'm going to be using in calculating the capacitance voltage using the step-by-step approach. Okay, so I redrew the circuit again. I made the equivalent capacitor open circuit, the switch open circuit. This now how the circuit looks like. My target is to calculate this voltage here. This is VC. This is the capacitor voltage at time t equal to 0 minus, just before the switch was closed. Okay. You have a situation like this one. You can, of course, you can do loop or nodal, but for this one, I feel that using a source transformation will be more appropriate. Why? Because this looks to me like one loop. But if I get rid of this current source and its parallel resistance, and I replace them by a voltage source and a series resistance, I will create only one loop. Okay, so I can use then the current the voltage divider to get the open circuit. So remember the equivalent voltage will be 1 milliampere by 4k is going to be 4 volts, and it's going to be in series with 4 kilo ohm. So this is what I did here. I got rid of this current source. I replaced it by 4 volts, 4k. The great thing about this is that this is now one loop, okay? And I'm looking for this voltage. But this voltage is the voltage across 2k and 2k. And I have another 4k. The total voltage around the circuit is 12 plus 4, 16. So this 16 will be divided into 8 between across this 4k, and another 8 across this 4k. Okay, we agreed that these two resistances 4k and 4k, they are equal. Then half the voltage will appear across this 4k, and half the voltage will appear across this 4k. So we know now that the open circuit, which is a capacitor voltage at time t equal to 0 minus, is a capacitor voltage just before we close the switch, is going to be equal to 16 divided by 2. Why did I divide by 2? Because the voltage division is 1/2. This is 4k and this is 4k. So we know now that the initial condition is 8 volts. We go back again and we redraw the circuit after we close the switch, and then we try to calculate the capacitor voltage at infinity. So the capacitor voltage at infinity means that the capacitor has finished charging or discharging, and it represents again open circuit. I notice that I do all my calculations on the equivalent capacitor, which is the combination of all these three capacitors. Okay, so I redrew the circuit again. The switch, as you can see, has been closed. I'm talking about steady state, so time going to infinity. So the capacitor, the equivalent capacitor, still looks like open circuit. And my target is to find this open circuit voltage. Why? Because I need the capacitor voltage of infinity to calculate the coefficients K1 and K2. Now, there are so many ways of solving this. I have two sources here. I have one loop, second loop, third loop. You can use loop analysis, but really, if you think about it carefully, you will see that this circuit has only one node, because this one is the same as this one, the same as this one, and this is ground here. Okay, so this one is the same as this one, the same as this one, while this is ground here. So I have only one voltage to solve for, which is V. Okay, so we try to apply KCL at this node. How many currents are flowing out or in how many branches? A branch, second branch, third branch, fourth branch, fifth branch. Okay, the current here is V over 4K. The current flowing out here is minus 1 milliampere. It's minus 1 milliampere because this is flowing in while I some currents flowing out. The current flowing out here is V over 2K. Now, we have not seen this situation before, but the current flowing out here is the same current flowing in here. Okay, I called it I1. So you can say plus I1 minus I1 is equal to 0. So I don't really need to include it. We have never had this situation before where a branch enters the same node. Okay, so you have this branch leaving and entering again, so it does not really affect our calculations in any way. Okay, so we get rid of this. So you multiply both sides here by 4K. So this will give you 4 plus 2V. So V plus 2V will give you 3V. This becomes 4 volts. You get that V is equal to 4 over 3 volts. So the voltage here, or the potential here relative to ground, is 4 over 3 volts. Now, I need to calculate V open circuit. V open circuit can be explained or can be written as this voltage plus this voltage. This voltage here is V. This is the voltage of this node here, okay? While this one here, I can calculate this drop. This is I1 multiplying 2K. How do I get I1? If this is V and this is V, so it is V minus 12 minus V over 2K. So it's effectively equal to minus 12 over 2K. So this is how I got I1. This is a very interesting situation because this is V and this is V. So the current flowing here is V plus 12 minus V over 2K. So V cancels and they end up only with minus 12 over 2K. So I1 is equal to minus 6 milliampere. Then V open circuit, which is the capacitor voltage infinity, will be equal to the voltage we calculated earlier, which is 4 over 3 volts. If you of course remember how we do this. If this is point A and this is point B, you want to calculate VEB, you draw a path that goes from B to A. Okay, so this is what we are doing here. I move from here to here, I get a positive voltage, negative positive, so this is V, 4 over 3. I move from here to get a negative voltage, so minus 2K multiplying I1, but I1 is negative. I1 is minus 6 milliamperes, so this will give me plus 12. Then we know that this voltage VAB, which is the capacitor voltage at infinity, is equal to 13.3333 volts. Okay, so now we calculated the second quantity we need for the step-by-step method. Okay, we have now to calculate the last parameter, which is the Thevenin resistance seen by the equivalent capacitor. The equivalent capacitor is here. Okay, and this is my circuit after the switch has been closed. I'm keeping the capacitor open circuit because I talk about steady state, but there is a capacitor here between these two terminals, the equivalent capacitor of value 400 microfarad. What is the input resistance seen by this capacitor? Well, this is the Thevenin resistance. In order to calculate it, you have to make this one short circuit, you have to make this one open circuit, and this is how the circuit looks like. If you take a look at this circuit, you will see that we have here this short, and this eliminates the 2K, and really the input resistance R7 is 2K in parallel with 4K. So 2K in parallel with 4K, it's 4 by 2 over 4 plus 2, so it's going to give you 8 over 6, so it's 1.333 kilo ohm. Then the time constant for the capacitor charging, this is charging R Thevenin multiplying C. The capacitance, the equivalent capacitance value, we calculated that's 400 microfarad. The Thevenin resistance here is 4 over 3K. If you multiply them, this is 10 to the power 3, this is 10 to the minus 4. So this will give you 16 over 30 seconds. Okay, so now we have all the information that we need to use the step-by-step method. So Vc of t is k1 plus k2 e to the minus 30 over 16t. If you make t goes to infinity, then k1 will be Vc at infinity, but this is 13.333, so this is k1. And we know that at time 0 the capacitor voltage was 8, then k1 plus k2 is equal to 8, but k1 already we know it's 13.333, then k2 is minus 5.333 as shown here. Okay, so now we have all the parameters for the capacitor voltage. So I wrote the expression for the capacitor voltage here. The last thing I should mention, this is the capacitor voltage, but we are not being asked for the capacitor voltage. We are being asked for I naught of t. Notice that I naught of t is equal to this voltage divided by 2K, but this voltage here is equal to the capacitor voltage minus 12. Okay, remember, if you take the capacitor voltage and you subtract from it 12, you get the voltage of this node. Okay, so you get the voltage of here relative to ground, and this is why I calculated this voltage. I said that I naught of t is equal to this voltage divided by 2K. But what is this voltage? It is the capacitor voltage minus 12. Okay, this is how I got it. Okay, divided by I wrote here 2K, but it's not really 2K. I wrote here 12K. It's actually 2K. This is what we have here is 2K, is not 12K. So this is a typo here in the video. Okay, this is a typo. It's 2K, is not 12K. So I wrote the expression for the capacitor voltage. I subtracted from that 12. 13.3333 minus 12 will give you 1.333, and this part will remain the same. If you divide this by 2K, this becomes 0.6667 milliampere. This one here becomes 2.667 milliampere. So this is the expression for the current I naught of t.